have you here. I'm Hansani and I will be your host alongside Tarishima. TechXplore is a session series by the Association of Computing Students at the University of Sri Jayewardenepura that aims to bridge the gap between academic learning and industry. Before diving into the session, we have a quick announcement. Every participant will receive an e-certificate. To get yours, fill out the Google form shared during the session and don't forget to submit it on time. So, let's dive into the world of quantum computing. Over to you, Tarshima.
Now it's time to introduce our guest speaker, Mr. Adhisha Gammanpila. He is the CEO of both Feynman Global and Quantum Tunnel Design Private Limited. His journey in software product development began in 2014, and since then he has been building award-winning innovations and has gained global recognition. Some of his notable achievements include placing second place globally at Oracle's most innovative mobile app competition held in Silicon Valley in USA. And then he has placed first place in human robot interaction in Spain and placed second place in human computer interaction at Cambridge University of UK. In 2019, he published one of Sri Lanka's earliest quantum computing research papers implementing an algorithm on an IBM quantum computer. We are deeply honored to have him here today as our speaker. Let's warmly welcome Mr. Adhisha Gammanpila to start off with today's session on quantum computing. Over to you, sir.
All right. Thank you very much, everyone, for having me over here. Tarushima, just a quick check. Is my audio and the visual all good?
Yeah, sir. Yeah, it's all
lovely. Awesome. Thank you so much. And first of all, thank you so much for the entire the panel of academics and the academia, and as well as the sponsors for having me here today. It's truly a privilege and a honor to be back at the university and talking to all of y'all. So that being said, let me get started on the conversation. And Tarushima, I'm not sure whether it's allowed for the students to ask any questions, unmute themselves. If so, please feel free to let them in, because I'm more than happy to have a quite a two-way kind of a conversation rather than just delivering a speech or a lecture. Prefer to have it more of like a conversation.
Yeah.
Lovely, awesome. So to start off, everyone, it brings memories, right? When I was also studying, we used to say at this time, sometimes coming after from the university, and we're tired and we join an online session, we attend and we learn. And I know sometimes it might be difficult, sometimes it might be engaging. Like us, but first of all, it brings a lot of memories. So I hope you all are working hard towards your goals. So that being said, these are some of the areas I'll be talking with you all today. So this will be a very, very oversimplified conversation about quantum computing. I'll touch base what is quantum computing, the applications in the industries, and also is there any relationship between AI and quantum computing, or I would say quantum AI, and can quantum computers outperform classical computers, and whether it's ready to use, whether you can use a quantum computer right now and get benefits, and whether it will replace existing computers that we use day to day, and the companies, and what is the future roadmap for quantum technology. So you could also prepare yourself, develop your career around quantum computing. So we'll talk about the roadmaps for it. And at the end of the conversation, I'll share a little bit about my company, what we do in terms of quantum computing. And then you can also, I'll share some tips about how to start learning quantum computing and some personal thoughts for us to wrap up. So that being said, everyone, I don't think I'm very much of a difference from you guys, because I'm also coming from same university, same faculty, or I don't know, these two faculties or departments right now, but still from the same culture. And graduated in 2019, and I also studied computer science. So it's again good to be back, and consider me as one of you guys, and let's have an engaging conversation around the topic. So yeah, so before we start off all the deep things about quantum computing, right now quantum computing is a very hot topic. Just to see how big is a hot topic it is, if you just look at the stock prices of quantum computing companies, it was skyrocketing few months ago because there were new innovations coming in likewise. So uh, even though quantum computing has been a topic right now, the earliest conversation started into around 90s when the scientist named Richard Feynman. So if you just search the person's name, Richard Feynman, you will come across with him, a Nobel Prize winning physicist. So once when Bill Gates was asked the question, who is your favorite teacher? Bill Gates said it's Richard Feynman. So Richard Feynman is someone like that who simplifies the most complex things and delivers to the world, especially around physics. So he's an amazing person that you could just search around and learn about his theories and what he has contributed with. Now, Feynman or Richard Feynman is the person who initially popularized the concept of quantum computing. Now imagine, so you are using your phone, you're using your computer. Now, when you do a complex task, let's say you run a machine learning algorithm, or let's say there are multiple tabs open in your computer or in your laptop, in your phone, whatever it is, it gets heated up, it gets slow, right? Gets stuck. That means there's a lot of heavy computation goes on and it gets slow. Now, more and more computational, when the computational complexity increases, the computers get stuck. Now, for instance, let's say you want to do a mathematical calculation on a computer, it's a very heavyweight task. Then we have to use supercomputers. Now, let's say we want to simulate some sort of a chemical reaction or some sort of a element in nature, it's getting much more complex. And then even the supercomputers can't do it. Then only Richard Feynman said, if you want to simulate nature, if you want to simulate quantum mechanics, you need to go quantum in terms of your computation. And that is how quantum computing came into the world or got popularized in terms of simulating nature through computation. So that became the popularized birth for quantum computing. Just like AI was still was there at that time with neurons sparking, concepts being built out, but it was not mass popularized until OpenAI popularized it with ChatGPT. Similarly, quantum computing is also at a time like that where ChatGPT was in 2017. So in the next 5 years, quantum computing is also going to get to the stage where ChatGPT or the popularity is in terms of that technology. So the wave is coming. So for you, it's the opportunity you are getting this 5 years ahead of time signal to prepare yourself. So if you're in the first year, start investing in yourself in terms of quantum computing. So by the time it becomes a popular subject, you will be one of the very first few people, or mostly most demanded people in the world for the subject. So that's the history and where the wave is heading. So what is this big topic, quantum computing? What is this whole gigantic thing about quantum computing? Let me touch base upon it. Um, Quantum computers are a different way of computing things. So we have the normal, we call it the classical computing. So we have things called bits. We have the bit. So it can be a voltage, low charge, and a high charge, or a 0 or a 1, how we abstract it. With these bits, zeros and ones, highs and lows, we create the entire computing or the computation that we do. It's out of 0 and 1. It's black or white, right? It's always either one. But when it comes to quantum computing, in physics, there is this thing called wave particle duality. That is, an electron or a particle can possess both particle as well as wave properties at the same time. So that is a superpositioning of two states. So this phenomenon has been brought into computing, and there's a thing called a qubit or a quantum bit, which can possess the states both 0, 1 and in between states at a given time. So how we represent it is with a sphere like this. So here we have the 0 state, and then we have the 1 state here. And in between, at a given point or in a given point in time, the bit or the qubit can stay in any of these superposition states. So this is hugely different when it comes to classical states as well as compared with quantum computing or quantum states, quantum qubits. A bit can hold 0 or 1 at a given time, but a qubit can hold all these states at a given time until it's measured. So this brings to a huge computational benefit when it comes to large computing, large calculations. For example, let's say 2 bits, right? If it's 2 bits, you have 0, 0, right? So let's say uh, let's do like a quick quick representation of this. Let's say we have 2 bits. So in a classical way, we have 2 bits, 0, 0, sorry, 0, 0, then it can be 0, 1, 1, 0, or 1, 1. So these are the possible states that a 2-bit system can have, right? Binary. Now, when it comes to qubits, if we look at a qubit, so it can be 0, 0 at the same time. 0, 0. It can also have 0, 0, 0, 1, 1, 0, and 1, 1. But the difference is all these 4 states, can be at a given moment. So in a classical computing paradigm, it's always 2 information. It's always, but when it comes to in a quantum computer, you can with 2 bits, qubits, you can represent 4. Now imagine you have 3 bits, qubits, you can represent 8. You can represent 8 information. Imagine you have 4 qubits, then you can represent 16 information with 4 qubits at a given time. So this is the superpositioning power that quantum computing is giving at exponential capability. Now let's say you have n-bit system, n-bit qubits. You will have 2 to the power n times of information at a given moment. So this is bringing a large amount of computational power. Let's say it's a 300 qubit system. Then it means 2 to the power 300. That means the amount of information can be mentioned or superposition at a given state. I know this can be a little bit confusing. It can be, what is this guy talking about? Yes, that is what it is. So 2 to the power 300 times of states can be mentioned at a system like that. So that means a lot of computation. 2 to the power 300 is all the particles in the universe collectively together. So that's huge. But just with 300 entangled qubits. So that is how the computational power is increasing when the number of qubits are added up. But this power is not there with a classical computer. That's why there are use cases over the history, over the last few years, where there are certain cases where quantum computers have outperformed classical computers in large. For instance, in 2019, Google did an experiment. They took their most powerful supercomputer and gave it a specific mathematical calculation. The estimated time for that supercomputer to finish that calculation was 10,000 years. 10,000 years for that supercomputer to finish that calculation. Imagine you run some sort of a program and it keeps on loading, and it says 30 minutes, 25 minutes likewise. Similarly, for that supercomputer to do that calculation, 10,000 years. And Google also used their quantum computer, programmed it to that specific question or that specific problem, and it was able to solve it under 200 seconds. Huge difference, right? So that is because it's that computational power that is being added up. Similarly, in China, again, a 200 under 200 seconds, which is estimated to take 2.5 billion years to complete by a supercomputer. That is almost, it can't solve that problem, right? 2.5 billion years, so under 200 seconds. And this has become a race now for countries, for companies to build a general purpose quantum computer so that they could do calculations very fast. It's all about calculations. Now, whether we can use this to watch YouTube? No, this is not a computer to watch YouTube. It's a computer to do calculations. It's like a calculator, but for complex operations. So before I go to the next set of slides, everyone, are we good with the way we are going ahead with? Is everyone clear up to now? Where are we, everyone? All good. All right. I'll just move on. No problem. Right. So, what sort of problems can a quantum computer solve? It can even help solve climate change, even those world scale large problems. It cannot solve global warming, but it can help solve things around it as well. Because it can help find a lot of big discoveries like material, simulations likewise. So it's all about calculations and computation. So now let's touch base upon few industries and some applications. Now, as I said, quantum computing is not to watch YouTube. It's not to do Photoshop designing. Of course, it can use to model certain things, but it's not just for us to write documents or likewise. In fact, if we just use it for day-to-day purpose, or if we try to do a day-to-day operation, it can be much more slower. Only where the places where we need to do high calculations is where this will come beneficial. For example, let's say you want to find an optimal number in a certain algorithm or a problem. Let's say in a stock market, you need to find a very optimal set of asset combinations. Now that is optimization problem. Now let's say you want to find a route which is the shortest path or the fastest route, then it's a mathematical calculation. So those are certain areas where people can start using, or where this quantum computing technology can be helpful. So this can be in chemistry, this can be in mathematics, this can be in financial industry, this can be in cyber security. For instance, all your the web protocols are encrypted and hashed. Even in blockchain, there is a hashing mechanism. So if somebody can quickly break the hashing and then replace it with another one, fixed like a malicious one, and keep on doing it very fast, the entire blockchain can be broken. So this is a threat from quantum computing. So cyber security. So these are some of the big industries which quantum computing can come into play. Now, if you look at chemistry, fertilizer discovery is a big use case. So if I'm to explain a little bit around it, ammonia. Ammonia is a major component in our lives. Because of ammonia only, all the food that we eat in mass scale are being able to grow in agriculture, because it's a major item in fertilizer. Now, this industrially created ammonia collects up to 2% of the global carbon dioxide emitted. So this is a huge problem for global warming, climate change as well. So everyone, if you're not aware of this global warming, climate change, guys, this is the biggest problem or the threat to your life in this generation or in this era of human civilization. Just to touch base upon it, if 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 uh, the increase of temperature increases by few decimals in terms of the current level, current averages, it will get into a irrecoverable state, which will completely bring out tsunamis, earthquakes, all those things. It cannot be reversed. So that is a huge threat in the world that is going on right now, because you will not see anything until it's next door to you, right? So it's happening in the ocean, it's happening in the atmosphere, everywhere. You don't see it because it's at a larger level, but now when it condenses into the nitty-gritties of the day-to-day life, it's going to be unstoppable. So when it comes to fertilizer production, again, 2% of the carbon dioxide emitted to the atmosphere out of ammonia production. But if you really look at it, in nature, it happens without any of this. Microorganisms get together, extract hydrogen and oxygen, and creates ammonia naturally, without any heat, without any pressurized processes, likewise, through enzymes. But the world, do they know it? No. The current world does not know how the microbes are doing it through enzymes, because they have not been able to simulate those chemical processes with the existing most powerful supercomputers that yet exist. So companies, even like companies like Google, they are trying to reproduce that enzyme through quantum computing. Companies like Google, Sundar Pichai has already stated a statement over the next few years, they will be creating ammonia out of quantum computing technologies in the lab. So those are huge discoveries. So when it comes to quantum computing, so you might be able to say that this is not for day-to-day use. This is complete for R&D. This is completely for scientific discoveries. This is completely to simulate nature. That's where the quantum word even comes from. So there is one big angle. And then climate modeling. When it comes to climate modeling, it can be any type of modeling. Let's say you want to model a certain system. You want to model something which has a lot of interactions. Say, so that is a place where you want to process a lot of data. That is where quantum computing can come into play. Now, for instance, let's say you want to climate model, you need to factor so many parameters with so many data happening within a millisecond. Huge computation. That is where quantum computing can come and contribute. Same for transportation. A lot of variables, a lot of factors to be considered. Imagine you are running a machine learning algorithm, so much of computational variations, and then you have to, cut off certain variables. Similarly, quantum computing can add those variables and find better solutions at a shorter period. So there is also another use case. Now, with all these things, you might be noticing I've been saying a lot on the word optimization, calculations. Now, if you have studied machine learning or neural networks in your course modules, or if you are to learn in the future, or if you just search on machine learning, it's all about running an objective function to maximize or find the lowest point. So it's all about getting that final point, reducing it, concluding it to an optimal number. Quantum computing is doing that calculation in another way. That is where the optimization comes in. And when it comes, AI is created out of machine learning capabilities. Machine learning does all those intelligent work, neural networks, how the brain works, likewise. So it's all about training the model through optimization. Now, you bring quantum compute into it, it will bring a different paradigm of computational power to train better models, to create better results out of AI and machine learning. So there's a new field coming as quantum AI and quantum machine learning. So on TensorFlow, if you search quantum machine learning, there's a separate set of examples how to start learning on quantum AI as well. So it's that fundamental principle of optimization, the optimization that comes in. So there is also another popular area that is coming into play. Right. Now, that being said, can quantum computers outperform classical computers? The short answer is yes, for computational aspects for calculations. But if the question is, can quantum computers outperform classical computers right now at this point in time? No. So we don't have production grade or ready to use kind of. I'm sorry about it.
Excuse me, sir.
Yeah.
Some students have raised some questions in the chat as well. Is it possible for you to?
Sure. Would you mind reading them out?
Yeah, sure.
Yeah, thank you.
So one has asked whether we can use quantum computing to solve unsolved mathematical questions.
Okay, I'll answer that. Okay.
And then, yeah, there's a request to explain the superpositioning once again, if possible. And then someone has said that in a previous slide, it has been said that it takes 2.5 year to solve it takes a problem that takes 2.5 billion years has been solved within 200 seconds. Someone has asked whether it is because of the complexity or the approach or the limitation of hardware.
Okay,
Those are the questions for now.
Great. So superpositioning this brief, and the first question is, can we solve unsolved mathematical problems? Lovely. So to answer the first and the last questions, then I'll go to the superpositioning. Whether we can solve unsolved mathematical problems, it's a very high probability to solve. Very high probability to solve. So there is a categorization of NP hard category problems. So it's not yet stated that it can solve, but it has been experimentally found that you can get better results rather than a supercomputer. So to give a short answer, whether you can find the equation to solve unsolved mathematical problems, I'm not credible enough to say a yes or no answer for it, but you can get solutions, better solutions than right now through quantum computers. That is a very high chance of achieving, because it's all about solving the equation in some sort of approach, which quantum computers are very much good at doing. So yes, there's a very high chance that unsolved mathematical problems can be solved or get very closer results, nearby results. So that is a very high probability. Now, to answer the third question, whether it's a hardware limitation, likewise, well, right now, if you are aware of it, there is a concept called the Moore's law. So if you just go on Google and search Moore's law, so it says that every year, the gap between the processing units are doubling, are getting into half and tripling up. I'm sorry, doubling up the computational power. Now it has been happening over the years, and now it's saturated such that the particles in a transistor are so close that the gap in between is showing quantum mechanical effects. And now the computational power cannot go beyond that, because you can't bring, like, let's say these are two semiconductor units. Let's say this is some years ago. Now they have reduced the gap, again reduced the gap, reduce the gap, reduce the gap. Now it has come to a level, if you further reduce, it's going to bring more quantum mechanical effects. It's going to bring more quantum mechanical effects. Hold on 1 second. 1 second, please. Sorry about it. The distance has come to a very short space that you can't go more computation, to have more computational power. So this has become a industrial challenge even for NVIDIA. Still, even with GPU, still that the fundamental aspect is there. Yes, there is a um, hardware limitation as well. At the same time, the way we do it is also a limitation. Imagine you are trying to do something in the same way and you're not getting results. Same. When we try to solve quantum mechanical things, or if you're trying to simulate nature through non-quantum mechanical aspects, we will not see those effects coming in. So that is also the way we solve it. So quantum computing is bringing a quantum mechanical approach, so we can simulate more quantum mechanical things, quantum mechanical effects. So if you want to simulate quantum effects, you need to have a quantum system. So quantum computing has that property in it, so you can do it and show, which a digital system cannot do. So that is also another aspect where we approach the problem in a different way. So these high durations are, one is definitely a hardware challenge, which the technology cannot go beyond that, or has almost come to a saturation, and as well as a different approach of solving them. Yeah. All right. Now, to answer the second question, just search this thing, wave particle duality. So what it states is that in quantum mechanics, let's say an electron, until you measure, it doesn't have to be an electron. Even us as human beings, at a given point in time, we are showcasing both wave and particle effects. Both wave and particle effects. Even us. The only thing is, when our mass increases, our wave properties decreases or becomes less significant, and the particle nature becomes more visible. So there's an equation for it as well. Now, similarly, when it comes to an electron, it is at its minimal state of a mass, and it showcases more wave properties. So at a given time, a particle can, or let's say an electron can showcase both wave as well as particle properties until you measure it. Now, why it is happening like that? So if you're a student who thinks, okay, why it is happening, if you discover it, probably it will be like a huge breakthrough, because those things are, to the best of my knowledge, are not yet discovered why it's happening like that. It is what it is. I think it's a paradox as well. So now this quantum mechanical idea has been brought into computing. There are the 0 and the 1 concept. So in a bit, you have the 0 and a 1. But in a qubit, at a given point in time, they have superposition it into together, so that it is between 0 and 1 at the same time. So you can do different operations on that and get the final result at a point of measurement. So that is a very high level answer to that, those three questions. Do we have any other questions? I'm sorry, before I move forward. And thank you so much for the questions as well.
No, sir, no question in chat.
All right, thank you so much. So can quantum computers outperform? Definitely yes, for calculations. And are quantum computers ready to use? Mostly R&D purpose, experimentally. The reason being, so if you look at a quantum computer, so what you see here is a refrigerator, right? This is a huge refrigerator. It's a huge refrigerator. And at the bottom of it, you have the quantum chips. And this operates at millikelvin. So 0. Millikelvin is the temperature. So let's say processor temperature. So it's almost close to absolute zero. So absolute zero, right? That is where no energy is there in that space. So that is the coldest point that the universe can have to the discoveries made so far. So at that millikelvin level only, these processors are running. Now imagine there is even a little phone signal, like even a phone signal is a microwave, right? It can go, that can be a noise, that can be a little bit of heat, noise, cosmic rays, radiation, anything. If something can go near the those cold quantum qubits, it can create noise and you will get errors. So for that reason, still people or companies have not been able to create general purpose, ready to use, error prone, error resistant quantum computers. So that is the where the currently world is. And recently, Microsoft released a new quantum chip, which is much more error resistant. So it is a race to create that quantum chip. So if that stage is achieved, it's a huge breakthrough in the world, and then it's another era of ChatGPTs and so on coming out. So keep an eye out. So are quantum computers ready to use? Not right now. Experimentally, you could try out. So let's say you want to try out quantum computing. On IBM, they give free quantum computing cloud access. You can start using it even right now, but it will have those technological barriers where it will not be able to outperform in great cases, in almost all the cases. All right. So can quantum computers be a replacement for classical computers? No. When I say no, it is for the day-to-day work, but for scientific work, it can replace the last bit of it where the highest amount of calculations are required. So 90% or 95% of the work will be done on a CPU and a GPU, and the most difficult part will be passed on to a quantum computer to process that and return it back to the classical computers. That is how the architectures are being designed right now. So we call them, not we actually, IBM calls them quantum centric supercomputers. So you have the CPU like this, the CPU services, and then you send it to GPUs, you do those calculations, and for the last bits, you send it to a quantum processor, then you process it and get it back. So it's getting all the best of both worlds, classical and quantum together to drive results. So this concept came like almost an year ago. So on IBM, they're also pioneers in quantum computing. Yeah, so that is around it. And going to the last parts of the conversation, who are the large players of quantum computing? IBM is a prominent company. Google, Microsoft are the popular ones. And Oxford Ionics is a hardware company. Rigetti is a hardware company. And D-Wave is known to be the very first quantum computing company in early 2000 who started building quantum computers. Right. Now let's get into the roadmap. Now, if you search on Google IBM quantum computing roadmap, you will see this roadmap being published. So here you have the innovation roadmap, and then you have the scientific and the data related roadmap or software related daily. Here you will see the years and what sort of innovation timeline it is having right now. So here you can see in 2024, the coding assistant, the platform development started. And here you can see the sizes of the quantum processors coming in. So this will be a good guidance for you to understand where the technology is. And also on McKinsey and Company, you can just search McKinsey and Company quantum computing roadmap. They have published 2023 and the 24 publications, which talks about the market as well as how the technology is evolving. Right. So everyone, I have spoken in very, very high level about quantum computing. Now, before I get to how you can learn as well as some stuff that we do, again, I want to see whether we have any questions, clarifications that you would like to have. If you don't mind, if there are any questions, can we read it out? Don't wait. No, you don't have to stay for the last minute. All right. Right. So let me get to the place what we do. Now, I don't want to make this statement, but yes, quantum computing is a little bit hard to use. The reason being, still the technology is at a point, or the coding capability is at a point where you have to program it with gates. Yes, there is you can use Python, you can use Qiskit from IBM as a framework, um, but it's still at a gate level programming. Now, this makes it a little bit hard because you need to know, you have to learn the frameworks, you need to know about the quantum information theory, a bit about quantum physics, likewise. So apart from subject knowledge for the implementation you're going to do. For that reason, we believe quantum computing is a bit hard. And also when I was also doing my final year thesis on quantum computing, I too faced the same challenge. And at a global scale, and which is also an opportunity for you, in 2021, there were 800 job postings for quantum computing, quantum scientist, quantum software engineer, quantum engineer, likewise. And only 290 like qualified students were there for those jobs. 290. So it's almost like 3-to-1 demand gap. Now imagine a world where there are more opportunities and there's less demand. How much of a value you would have? So this is a point which you could leverage. So you can start learning quantum computing on your own. Look for resources which I will also share to bridge this gap and to create this opportunity for yourself. So what we have done to solve this problem, so this is what we have done. So we used an LLM to create quantum computing code generation. So you could easily implement quantum computing solutions or R&D with it with our copilots. So I'm pretty sure you are aware what a copilot is. It's a coding assistant. It generates code, automatically deploys to quantum devices, and it can be fine-tuned with natural language, and also it can do it iteratively. So we make quantum computing easy to use. So here on the red, what you can see is all the manual steps that you have to do in terms of deploying a solution onto a quantum computer. Now with Feynman, what we do is we automate the entire process with AI. So so there is a picture of the screenshot. I'm sorry, a screenshot of the application we have been building completely for quantum computing. So it's all about making things faster. You can do it sooner, and you don't have to have a lot of background knowledge to implement quantum solutions. So if you know your subject area, and you can tell, just like on the Iron Man movie, hey Jarvis, do this, do this, do this. Similarly, it will do the exact requirement you'd need for a quantum computer on a quantum computer. So that is the experience we are trying to create. So the quantum computer startup we are building is at a very early stage. So it's out of London. Uh, so it's called Feynman, or as a tribute to Richard Feynman as well. Very, very early stage. And yeah, right. Now coming to the last few slides, how can you learn quantum computing? So very easy. So on YouTube, there's a million of things, content to learn, read and learn. But I would like to refer you to one proper reference, that is IBM. IBM is providing quantum computing learning. So you can visit IBM Quantum Computing Learning and explore their courses. It's free. You can try it out with the infrastructure. You can get started. And they also teach the mathematical part as well. So that is one option. So you just go search IBM Quantum Learning. You will find the results. Now, I've also followed it, and I know it's very good. That's why I recommend it. And I feel like there's more improvements that can be done. For that reason, we are also launching a quantum computing course completely free for all the students, which you can also log in and use, as well as try our quantum computing co-pilot. So after the session, I will share with the organization or the organizers a Google form which you can fill in and get access to the course material as well as the quantum co-pilot to R&D with it. So that is how you can get started on in terms of learning. One thing, IBM, and IBM has this framework called Qiskit, open source. You can learn it and get started. So that's like 90% of most of the things. There are other things like Microsoft has Q Sharp, um, which is for quantum computing, and Google is having something called Circ, which is also fine, but mostly the most popular one is Qiskit. So try to contribute to their GitHub repository likewise. So that is how you could get started on in learning. Right. Now, this is the end of the conversation around quantum computing, everyone. So for the last few minutes, I actually wanted to reserve some space since you all are undergraduates and to share some of my personal thoughts to inspire you in terms of some of the learnings I had in my journey. The first thing I wanted to share is have a great vision for yourself. So I think there's around 50 or 77 people over here, students. Have a great vision for yourself, for your life, for the people around you, for the country, to the world. Have a great vision and let your vision become your North Star. Make all your decisions around that larger vision that you have for yourself, for the world around you. Because when you have that vision, only all your career choices, everything that you do, everything that makes you confusing becomes extremely clear when you have a clear vision. For me, it's to move the world forward. That's it. So I want to build groundbreaking things in my companies, in the work I do. Things would exponentially move the world forward. Things that took 1 year can be done, to 10 years can be done in 2 years, or the things that were thought impossible can be done, so that the world keeps on moving forward. So at least to make the world one step forward if I was not there. So have that larger vision in yourself on what you want to do, what you want to contribute to the world. So have that vision. So that becomes your North Star. From an early stage, I was fortunate enough to meet people who inspired me to have that vision, to create a vision for myself. So have that vision in you, make your life choices with that. Then, even though it sounds not so obvious, it can be contradicting, but still it will be very much obvious for you because you have that clear vision or the North Star for you. Have that vision. Number two, ask for help. If you're doing something big, you need help. Ask for help. Reach out to people. Ask for help. One of the biggest things that people don't do is asking for help. Ask for help. Have a vision. Ask for help. Number three, help without expecting. Just like you ask for help, make sure that you also help others. What you give is what comes back. Givers gain. So have a vision, ask for help, and also help others without expecting anything. And final thought, get bored. Get bored being common. In every aspect in your life, just think, how can I make this a little bit special? How can I make this a little bit unique? How can I add more value to this? Even if you're doing an assignment, how can I make it special? How can I add a drop of magical thoughts so that I can make it innovative? Get bored being common. Get being bored being common. Right? Just think, how can you make it unique? And one last thing, after lectures, don't download movies from the university Wi-Fi and watch them in the night, or just don't go to the Sky Cafe or to some other cafe and just just slave around watching those movies or chit-chatting, because your time is limited. Because if you are a person with a great vision, and when you want help, and when you're also helping others, and when you're also doing something innovative, you don't have time to do these things. Right? Save your time, work on greater things. Time is limited. So when you have all these things, so with these things in mind, but having a greater vision, asking for help, help others and being bored of being common, doing new things, this will really, really align you to do big things in life. So you can start small, think big. You can think big, you can start small, and you can also work really, really fast. So those are the final thoughts. So again, thank you so much for having me here. More than happy to answer if there are any questions, everyone. The organizing committee, over to you.
Yes, sir. There are.
Thank you, Mr. Adhisha, for the insightful session. Actually, it was a very insightful session. Guys, now it's time for a Q&A. Before we begin the Q&A session, take 5 minutes to submit the Google form to secure your e-certificate. And also, if you have any questions, drop them in the chat, or you can unmute your mic and ask the questions. So there are 2 questions already in the chat.
Okay, I think there's a question by Tekshan about the community. Tekshan refers the IBM quantum learning, and they have the Discord channel. They have the entire community, the Qiskit community, to help you around this question. So that will really add value to you. IBM quantum learning. So once I tried to replace my ML algo using Circ, but I couldn't achieve the desired output. Could you please share a demo how? Okay. At the moment, I will not be able to show you a demo, but I can give you an insight. Rather than using Circ, just try Qiskit, because yes, Circ has a lot of libraries, but Qiskit has a bigger community to the best of knowledge I have. So try using Qiskit, and yes, that could happen. You will not achieve desired results because the technology is a little bit too early. Maybe you will not be able to run certain epochs you want to run, so forth. Uh, because that's the real experience you are facing, Rushira. But congratulations again for trying this wonderful area. Yes. I think that's all the questions. If I'm more than happy to answer if there's anything else. And again, thank you so much for the organizing committee. I mean, fantastic organizing. I mean, like, love the way y'all have set it up. Great hospitality. And again, please do pass my thanks to the academia as well as the sponsors around for having me here. Really appreciate it. And all the best for the association to uh, keep on doing wonderful things. So I was also part of my society at the university back in the day. So I know how hard it is for you to organize these events the time after university. So good job to the organizing committee as well. Really appreciate it.
As there are no questions, over to you, Tarishima.
Thank you, Mr. Adhisha, for sharing your expertise with us today. We truly appreciate your time and insights. And as a little token of our gratitude, we have a small appreciation gift for you. Your contribution to TechXplore 1.0 means a lot to us. And once again, thank you for being a part of this session.
My pleasure, everyone. My pleasure. Thank you so much. Let's keep in touch. And I'll send the form as well, where the students can get access to the quantum copilot we are building, as well as the course content we are creating for free of charge. Yeah.
Sure. Thank you, sir.
All right. All right. Thank you very much, everyone. Have a good night. Bye-bye. See you.
Good night. Guys, here is an exciting news. We have more amazing sessions coming up on April 4th, game development, and on April 7th, financial technology. So stay tuned for update and don't miss out.
As we wrap up, a huge thank you to Mr. Adhisha Gammanpila for sharing his knowledge. And thank you to our participants as well for your enthusiasm, and to our organizers for making this event possible. And special thanks goes to our sponsors for supporting TechXplore 1.2. And with that, we can conclude our session and hope to see you all at our next session with a similarly intriguing topic. Have a great night. Thank you.